So two important topics we are going to address today. One is nominal and effective interest rates. I'm going to define them, show you why they're important, their significance, and I'm going to also go over a few problems showing that how we can actually do equivalence calculations using effective interest rate. The nominal interest rate, we're going to again discuss it today. So the focus is if payments occur more frequently than annual, how do you calculate economic equivalence? In other words, if we have more than one payment per year, then how do we calculate economic equivalence? Because of the change in the interest rate that is associated with that. When I say change in the interest rate, it's not really a change, it's rather an adjustment, but we're going to see that shortly. If interest period is other than annual, how do you calculate economic equivalence? And again, this applies to both commercial loans, debt, and also personal loans. So let's put things in perspective. Let's take a look at nominal versus effective interest rates. Again, it's very important for you to be able to tell the difference between nominal interest rate and effective interest rate. These are the terminology that you need to master as we go through the course. So the nominal interest rate is the interest rate quoted based on an annual period. And we've seen that from previous lectures. What is an effective interest rate? Is an actual interest earned or paid in a year or some other time period. So an example, you probably heard the term APR, annual percentage rate. Again, APR stands for annual percentage rate, or annual percentage rate, APR, the way, different depending on different pronunciations. But if it is compounded monthly, it's going to be different than if it's compounded on a yearly basis. Again, things will become more clear as we go through the lecture today. So let's take a look at what it really means to have 18% compounded monthly. There is an interest rate of 18% given or defined, and it's given that it is compounded monthly, but what does it really mean? So what it really means is that the common sense would tell you in order to calculate the interest rate per month, you would simply divide it by 12, right? Well, that would bring us to 1.5%. And again, that would be, since we divided by 12, and that's going to be number of interest periods as 12, right? So far, we have no problem. So each month, if we borrow the money according to this interest rate from the bank, each month the bank will charge 1.5% interest on the unpaid balance, right? Unpaid balance, if the money is borrowed. And if you will earn, meaning that you would, if the interest rate is a deposit that you made, the interest rate is on a deposit, then you will earn 1.5% interest each month on your remaining balance if you deposited monthly, right? So far, so good, right? So let's take a look at this to have a better understanding of what is going on. So for that 18%, we just divide that by 12, and we come up with 0.015 or 1.5%. One thing in this class that you really need to quickly be able to calculate it, like a mental calculation, is what would the 1.5% become? I still see that some people, they have problem with 1.5%. That is simply 1.5 divided by 100. So you divide 1.5 by 100, or 1.5 by 100, you would get 0.015. Again, this is the 15% that is monthly, calculated monthly. So if you do the calculation using the formula that we discussed last time, future value is P multiplied by 1 plus I to the power n. Again, suppose that you invest $1 for 1 year at 18% compounded monthly. How much interest would you earn? This is how we get confused over these interest rates by not using these formulas. If we follow the calculations, again, there's no magic involved with this. Your $1 would become 1.1956. So that is really not 18%. It is 19.56%, right? So where does that 1.56% extra come from? Well, that is the power of compounding, and because of the power of the equation, we take the parentheses to the appropriate power. In this case, it was 12. We pretty much come up with this number. So in reality, the 18%, if it is calculated monthly, whether it's on a debt or whether it's on money that is earning interest, as you can see, the 18% could easily be calculated to, could be converted to 19.56%. The real interest rate in this case is 19.56%, not 18%. So what happened if we increase this number up here? Instead of 12, what happened if this number is 365? In that case, that means that the number of interest period would be 365. In that case, we divide 18 by 365, and we continue with the calculations, and 19.56% would be even higher in that case that I just discussed. So the effective annual rate or yield is simply calculated using this formula. In this formula, R is the nominal interest rate per year, and capital M is the number of interest periods per year, and I sub A is the effective annual interest rate. So similar to what we've just showed you so far, we formulated now, and we would calculate the effective annual interest rate. And as you have seen, we use this formula, and the real APR turned out to be 19.56 compounded annual. So let's take a look at a practice problem, and we take it from there. So let's take a look at this particular problem. In this case, you can read it together and try to digest it and solve this problem. So if your credit card calculates the interest based on a 12.5% APR, what is your monthly interest rate and annual effective interest rate respectively? So what is the monthly interest rate and annual effective interest rate respectively? Then your current outstanding balance is $2,000 and skips payment for 2 months. So with all the interest information that you have and with the monthly interest rate, we are going to first calculate the monthly interest rate, and we're going to calculate the annual effective interest rate, and then we are going to assume that the outstanding balance is $2,000. We skip payments for 2 months. Then what will be the total, the balance 2 months for now? You probably read the statistics. More than 60% of Americans, they have credit card debt. This problem is a very practical problem to show you how to manage some of that debt, and that's associated with credit card. Again, each of us, we may be able to relate to this. So the monthly interest rate, I, is 12.5%, and that's an APR. We divide that by 12 to get the monthly interest rate. So far, really no problem. We just did a simple arithmetic. Then we would calculate the annual effective interest rate, simply using the formula that I just introduced you to it, and 12.5% divided by 12. Again, 12.5% is really 0.0125. So it's very important to understand that it's 12.5 divided by 100. And if you divide that by 100, you're going to be 0.125. So at 1.0417%, the annual effective interest rate. As such, we simply take this to the power of 12. As the problem stated, the I sub A would be 13.24. That is an effective interest rate. So let's assume that there is an outstanding balance of $2,000. And we would like to know what would be in the future value after 2 months, and what would be the outstanding balance. In this particular case, the interest rate was pretty moderate in today's terms, and what happened here is that that $2,000 would translate into $41.88 extra, so the future value would be $2,041.88. This is again the interest rate of 12.5% per annum for 2 years. There's no other way to do the calculations here, and this is the only correct way that we can come up with this. Now, the only thing that we introduced to you today here in this particular slide is the if F given P, and that's the tables in the back of your book. Study some of those tables, and you would be able to see the multiplication factor as a result. So in the back of your book, there are tables for F given P, and for F given P with a particular interest rate and N of 2. You should be able to get a factor. If you multiply that by 2,000, the answer would be $2,041.88. Okay, so that's really the bottom line for this particular problem. So let's take a look at another practice problem here together. So suppose your saving account pays 9% interest compounded quarterly. Throughout these problems, these numbers would change monthly to quarterly, annually. Again, we are going to play around with these numbers to show you different way of calculating it accordingly. So if you deposit $10,000 for 1 year, how much would you have if the saving account pays 9% interest compounded quarterly? So you can actually guess before I start the solution of this problem. My system is a little slow today. I'm trying to make it work, optimize it to the best we can. So let's take a look at the solution. The interest rate per quarter is per quarter. So right away we divide that by 4. 9% is 0.09 divided by 4 is 2.25%, or 0.0225. The annual effective interest rate in that case would be, according to the formula that I just introduced you for I sub A, 1 plus 0.0225 to the power 4 minus 1, 9.31%. Would you believe that before you took this class? If I tell you if you would have had an interest rate of 9% annually, or APR, it's going to give you more than 9% at the end of the year if you pretty much use the compounding formula, and if the interest rate calculated per quarter, well, based on my experience, most of you would say no, but some of you guys would say yes, so that's a good thing. So part C, $10,000 at the end of 1 year. Remember, every time we talk about the future, we're talking about F. That's the future value. Balance at the end of 1 year after four quarters. If we deposit $10,000 now, $10,000 today, what would be the balance at the end of 1 year with the information on the interest and the way it's being calculated? So again, if you go to the back of your book, there are tables that give you the values for F given P at 2.25% interest, and the number of times it is actually going to be calculated. So it's important for you to be able to work with these formulas. It's really a straightforward process, and I really don't see the need to go over it in these lectures. It's pretty straightforward. Just study some of the tables in the back of the book, and you will see how convenient that is. So 10,000 multiplied by a factor that's given in the back of the book. Eventually, the calculations, the $10,000 will be $10,931. Again, the significance here is that what's the way we the number of times that the interest is calculated. In this case, it was 4, and the interest rate itself, and those are two very important factors that pretty much dictate the results in this case. So I would like to bring your attention to this table that I provided you here with. It's the nominal and effective interest rates with different compounding periods. It's shown here as a matter of a comparison. Let's take a look at the 5% and 10%. We can start with a 5%. 5%, if it's compounded annually, it's going to be 5%. If it's compounded semi-annually, it's going to be 5.06%. If it's compounded quarterly, 5.09%. If it's compounded monthly, it's 5.12%. If it's compounded daily, it's going to be 5.13%. So next time you receive your credit card statement, please take a look at the fine print on the back of it or the front of it, and see how often the interest rate would be calculated on unpaid balances, and that would help you understand and develop some of the money management skills that otherwise you would have missed. Let's take a look at the 10%. If it's compounded annually, it's 10%. If it's compounding semi-annually, it's 10.5%. If it's compounding quarterly, it's 10.38%. Compounding monthly is 3.47%, and compounding daily is 10.52%. So as you can see in this case, it's really a 0.5% difference. Think about millions and millions of dollars that would be affected with such a method, from compounding annually all the way to compounding daily. And these are again some examples that the examples that we went over. The example of $10,000 just being tabulated here to show the difference between different quarters. Okay, so why do we need an effective interest rate per payment period? That you might have already thought about this, and you may already have the answer, but Why do we really need an effective interest rate per payment period? The first thing that comes to your mind is, yeah, because the banks would like to charge more money. Well, that's one answer. I don't want to discuss that particular answer, but again, let's take a look at the differences between the payment period and interest period if they are not the same. If they're the same, the problem is really solved. But what if the payment period and the interest period are not the same? Again, these two bars down here should provide you with a straight comparison. As you can see, there will be if the payment period is greater than the interest period, then there would be some kind of a gap here that is difficult to cover. And if you also look at the other case down here, the last one that I put an X mark right next to it, if the payment period is shorter than the interest period, then what? Then how would that get paid? Again, it's going to any other way that we currently have and propose for the future must be able to answer that particular question. What if the length of the payment or the payment period and interest period, they are not the same? What if one is longer than the other and vice versa? And that's why we need an effective interest rate to be able to accommodate for those scenarios. So again, the formula effective interest rate that you've seen, we need to modify a little bit to come up with the effective interest rate per payment period. As such, as you can see here, the formula is given in the green bracket here inside the green. So that's the formula. So again, in this formula, the unknowns are defined as such. C, capital C, is number of interest period per payment period. Capital K is number of payment periods per year. CK, capital C multiplied by capital K, is the total number of interest periods per year. Or M, again, you can, we've already seen this, so that'd be R over CK is the nothing but M, capital M, and R over K is the nominal interest rate per payment period. Let's take a look at the different numbers here. One of the examples that I can discuss with you here is the 12% interest rate, in this case compounded monthly, and the payment period is per quarter, and the compounding period is month. Now we have three different things here. One is the 12% compounded monthly. Then the second thing is what will be the payment period? In this case, quarter, and the compounded period is month. In that case, first we need to calculate the effective interest rate per quarter. That is the way it's shown down here. This is how we make the calculation. So far it's pretty straightforward. And then effective annual interest rate. In this case, again, we use the formula that was just introduced to you. And if you want to calculate I sub A, then in this case it's going to turn out to be 12.68%. That's the effective annual interest rate. If you want to use the formula that I just introduced you, you should be able to get the same result. This is just the formula that we just see, subtracting it 1 from minus 1, subtracting 1 from the right side of the equation. That's it's going to be I sub A. So both should give the same results, really. So I'm going to introduce to you a new concept here, and that is the continuous compounding. I underline it here with red. We so far introduced you to compounding per a period. The term continuous compounding, as shown here in this simple mathematical description, the continuous compounding is as C, capital C, approaches infinity in that particular equation that you see up here in this bracket. As C approaches infinity in this particular problem, we need to take the limit. So I would be the limit of 1 plus r divided by ck to the power c minus 1. As c approaches infinity, we take the limit of this equation, and the limit of that equation would be e to the power r, close parentheses, well, e to the power r would be inside parentheses to the power 1 divided by k minus 1, and that would give us the interest rate if the compounding is continuous, or effective interest rate per payment period with continuous compounding. So the different cases I would like to discuss with you here. This is the first case, or the first, so I call it the case 0. In case 0, let's assume that we have 8% compounded quarterly. The payment period is per quarter, and the interest period is also quarterly, so they are the same. So the interest period is given at 8%. There are 4 payments per year. Capital C is 1. That is the interest period per quarter. Remember, the interest period is also quarterly, so they're the same. And M is the periods per year. In this case, the number of interest periods per year is 4, so capital M would be 4. And as such, for an 8% compounded quarterly, the interest rate would be 2%. Or we could have simply divided 8, since the payment period and interest period, they're the same. Then we could have simply divided 8 by 4, and we would get 2% per quarter. That was also a perhaps more straightforward answer. But I avoided that because of what you would be seeing shortly. So, case 1, still 8% compounded monthly. In this case, the payment period is quarterly, but the interest period is monthly. So, as you can see, the payment period and interest period, they're not the same anymore. So, in every quarter, there are 3 months. The payment period would be that entire quarter, but the interest period would be monthly. Now, the situation would be somewhat different, and I wanted to demonstrate this using the equation. That's why we try to avoid the simple method in previous case, in case 0, to demonstrate the application of the equation and how it would affect the answer. So, in this case, R is 8%, K is 4 payments per year, and the interest rate, interest periods per quarter, there are 3 of them in one quarter, since this interest period is monthly. And capital M is 12 interest periods per year. So, if you make mistakes in any of these problems, in calculating any of these problems, the answer would be erroneous. So make sure that you do this calculations correctly. Again, it's practice that you can do this kind of calculation. So case 2, the interest period now became weekly, and that means 13 interest periods per quarter, because of 3 times 12 plus 1, right? Because we want to make sure we calculate that. Most mistakes that people make is in a problem like that, they assume C to be 12. I've seen that too many times. Whereas in reality, it is really not 12 or 13 interest periods per quarter. If you count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So if you start counting this, you would see that in the first quarter, because the interest period is at the end, in this case, it's weekly. It's at the end of each week. You end up with 13 weeks per quarter, and that would translate into 52 interest periods per week. And as such, you do the calculations, I would turn out to be a little bit more, right? So the first one, 2%, and case 1, well, case 0, 2%, case 1, 2.013%, and case 2, 2.0186%. And as you can see, the numbers will keep increasing because for case 1, the interest period is continuous. We need to take the limit of the formula that I just shown you previously. In the green formula, I call it. Green stands for money, and as such, if there are infinite interest periods, then we follow this equation, and the interest rate will be 2.0201% per quarter. And this table should provide you with a comparison of what I have just covered. That brings me to the end of today's discussions.